Hello and welcome back to CS Student Advanced Data Structures and Algorithms of the Department of Computer Science, UP Diliman. This lecture is about analysis of recursive algorithms. So recall that we presented insertion sort and merge sort from the previous module. Basically, for this lecture, we will give more details about how we can compute for the actual running time of insertion sort using our techniques from lecture 2.1, and we will also present the analysis of recursive algorithms in general. So we have a step-by-step process also for counting the total number of basic operation execution. So we will present one method, which is backward substitution. We're already familiar with the partition tree, so we will also present a more detailed explanation of partition trees here in this lecture. Okay, so let's start with the problem of sorting. Again, we have the input and the output specification. For the input, we have a sequence of numbers, and for the output, the requirement is that it's a permutation with this condition. So an example input instance is this number, and the output is a valid output because it obeys this condition. Okay. So the first algorithm is the insertion sort. We showed an example in our previous module how it works. So the code is um, to perform an insertion of a particular key to the correct location of that key. So let's try to analyze the algorithm using what we've learned from lecture 2.1. Okay, so the first thing we need to do is to identify the input parameter. The input parameter size here is the size of the array A, which is n. And then for the basic operation is key comparison. Okay, so the next step is to identify actually whether we will choose best, average, or worst case. In this analysis, we will consider the worst case. Okay, so the next thing to do is to set up the summation, and the summation is by checking the bounds of the for loops. So the first loop is for j equal to 2 up to n, and then the second loop is for I equal to starting from 0 to j minus 1. And then the count of basic operation inside the loop is just 1 because we needed one comparison. Okay? So we can simplify this by first evaluating the summation, getting the closed form. We can get the closed form by following the formula for simplifying this one, which is j minus 1 minus 0 plus 1, which is just this one. The formula for the closed form of this summation is this one, so we can just follow this form and we can get n squared plus 2n over 2. So this expression is actually in theta of n squared. So yeah, the running time of insertion sort is theta n squared. Okay? So for the worst analysis, theta n squared is the running time of the algorithm, and that is for an input that is in reverse sorted. For average case analysis, we can use the technique used to compute for the expected number. Using that technique, we can compute for theta n squared as well for insertion sort. For merge sort, just to recall, this is a recursive algorithm that performs merging of the first half and the second half. Okay? With the base case na if it's an array containing one element, sorted na yun. And then another step, which is merge. What merging does is, given two sorted lists, it outputs a single list na containing all the elements nung dalawang sorted list. Okay, so this is an example of merge sort for this input instance. So the first half is here, the second half is here. We perform merge sort recursively until maging single element na lang. And trivially, this part is already sorted. So we will perform merge in the next operation. Merging is done this way as shown in the previous lecture with a running time of theta n, where n is the total number of elements nung final sorted list. Okay, so this is how we merge from bottom to the top approach. So yeah. So how can we analyze merge sort? Again, we still count the total number of key comparisons. But instead of setting up a summation, we set up a recursive relation for the running time. Okay? So how can we set up a recursive relation for the running time? We have T of n as the running time of merge sort, and it is equivalent to the running time of recursively sorting the first half and the second half. So that's equivalent to 2 times n over 2, so tigkalahati sila, plus something else. And that something else is for the merge part. Okay, so here we have an input parameter na n, and the basic operation is still key comparison. We're still counting the total number of key comparisons. So for the recursive relation, the total number of key comparison for n equal to 1 is theta of 1, or simply 1 lang. For n that is greater than 1, so sa non-trivial case, we use the merge sort, or the total number of key comparison for n is 2 times the required running time to sort half of the elements plus the running time of performing the merge. Okay? So now that we have a recursive relation for the running time of merge sort, what we need to do is to compute for the recursion tree. So yung previous na recursion tree natin looks like this. Okay? We can basically count the nodes of this tree to get an idea kung gaano kadami yung basic operation. Sa previous lecture natin, we established the n log n as the total number of steps necessary for merge sort. Yeah. So let's have another example. So the problem is the evaluation of n factorial. So by definition, n factorial is equivalent to this form. So yeah. And this is for n greater than equal to 1, and for the base case, we have 0 factorial, which is equal to 1. Okay, so this definition is actually recursive then, because we can represent the factorial of n by using this. So f of n for the base case is 1 if n is equal to 0. Otherwise, if n is greater than equal to 1, the value for n factorial is equivalent to n times n minus 1 factorial. Okay, so this recursive definition is important later on, how we can define an algorithm that exactly computes this one. Okay, so this is the recursive algorithm for computing the factorial. Again, what's the input parameter? We have n as our input parameter, at hindi lang single, kahit na one number lang yung input. And then the basic operation here is, let's look, multiplication of two numbers. Okay? And then we have to set up a recurrence relation, and that recurrence relation is the count of basic operation, or the count of the required multiplication. No? So for the base case, if n is equal to 0, wala namang required na multiplication. Okay, that's why we have 0 here. And then for n greater than equal to 1, we have 1, which is you required to compute for this one, plus the required number of multiplication to compute for n minus 1 factorial. Okay? So now that we have this recursive definition of the running time, we can compute the closed form of this one. Okay? So instead of creating a tree, we can solve this by backward substitution method. The backward substitution method goes like this. For this one, we can substitute the value of t of n minus 1 by something na using the recursive definition. So, we know that t of n minus 1 is equivalent to t of n minus 2 plus 1. We can simplify this and we can represent it by 2 of n minus 2 plus 2. Okay, so next is we substitute t of n minus 2 naman using t of n minus 3 and so on. So if we try to do it for t of n minus 4, minus 5, and so on, makakakuha tayo ng pattern how we can represent t of n in terms of I. So in this case, we can generalize it by t of n minus I plus I based from the sequence of backward substitution. Okay, so the next thing to do is to identify for which value of I maaabot yung base case. So, for n minus I equal to 0, we can solve I in terms of n. So, we have I equal to n. So, in this case, we can simply replace this part by replacing the evaluation of t of 0 by using the base case na 0 plus the value of I based from what we computed here. So, for I equal to n, magiging 0 Cn minus I. So, we have n. And then, we're done. So, we obtained the closed form for this recursive formulation. This method is called the backward substitution. Okay? So, let's try to list down these steps necessary for analyzing recursive algorithms. Actually, for the first few steps, similar lang siya for the non-recursive algorithms. But for recursive algorithms, ang difference is we will set up a recurrence relation instead of a summation. And then we solve the recurrence. And there are different ways to solve the recurrence. We have the partition tree method na parang we try to create the recursion tree and count the total number of steps per node of the recursion tree. Or we can use the backward substitution. Okay? Meron pang other methods that we will present in lecture 2.3.